We were unable to finish all the examples in class for the expected value notes, so I'm going to go ahead and rework the examples. I know we did a couple of them, but I'm going to go ahead and rework them just in case anybody was absent or if you just want to see them explained again quickly. So number one, it says determine the expected value for the probability distribution defined below. So in the notes above, it says that expected value is the sum of all your x's times their probability. So we want to multiply each of our x's times its own probability. So 1 would be multiplied by 0.3, 2 would be multiplied by 0.2, 3 would be multiplied by 0.4, and then 4 would be multiplied by 0.1. And then the notation tells you then to add them together. That means sum. So we want to say plus between each of those. And so there's a couple of different ways you can do that. I'm going to demonstrate the way I've written it on the calculator, but that's not actually how I would do it. Okay, so I would just do, I'm going to show you this way, and then I'll show you how I would really do it. So do 2 times 0.2 plus 3 times 0.4 plus 4 times 0.1. So I'm just going to double check, make sure I have it all typed in good. Typed in well, everything looks good. Okay, and run it, and so that's $2.30 or 2.3, depending on what the data actually represents. They didn't really give us a scenario, so I'm not quite sure, but the expected value would be 2.3 from that data. But again, that's not really how I would input it in the calculator. What I like to do in the calculator is use my list. So I would go stat edit, and in list 1, you want to put your x values. So I would do 1, 2, 3, and 4. And then in list 2, you next to each of those x values, you would want to put the probability of each of those values. So I have 0.3 for my 1, I have 0.2 for my 2, I have 0.4 for my 3, and then I have 0.1 for my 4. So you want to just double check it, make sure everything's typed in correctly, and then you go stat, over to calc, press enter because we want to do the one variable stats. We have our data in list 1, we have our frequency in list 2. So in order to get an L2 under a frequency list, you want to do second and then 2. And then we want to go down to calculate, and X bar will always be your answer if you use the list and run it this way. So X bar is the 2.3. That's called the weighted mean, which is your expected value. So expected value and weighted mean, those are the same thing. Okay. Number 2, determine the expected value for the number of heads and 2 tosses of a fair coin. Well, we have to think about what we could possibly get when we're tossing a coin, okay? So our possibilities are I could get 2 heads, I could get 2 tails, I could get a head and then a tail, or I could get a tail and then a head. Those are the only 4 possibilities when I'm flipping a coin. And so the number of heads I could get 0, I could get 1, or I could get 2. So how often did I get no heads at all? No heads at all would just be this event right here where you get 2 tails, and so that's 1 out of 4, which is 25%. Okay, and then how many times did I get just 1 head? That's this one right here and this one right here. So 2 out of 4, so it's 50% of the time that I got just 1 head. And then the last option is if I got 2 heads, so that would be this one right here, and that's 1 out of 4 again, so that's going to be 0.25. And so looking at it, these are the x's, and this is the probability of those x's. And so I want to do stat, edit, and I like to clear my lists out. So I'll just go up to where it says L2, hit clear, and then enter, and it'll wipe it out for me. And then go up to L1, hit clear, and enter, and it'll wipe it out for me. So my x values are either 0, 1, or 2. And then the probability of 0 is 0.25. The probability of 1 is 0.5, and then the probability of 2 is 0.25. Stat calc, one variable stats. Since I've already done this process, you'll notice that list 2 is in my frequency list. So I really don't have any changes to make there. I just calculate it, and you can see that I have an expected value of 1. Okay, so expected value for this scenario would be 1. And so kind of conceptually what that means is if I flip 2 coins, a lot of different trials, like I did it over and over and over and over, on average, I would expect to get a heads 1 time for the majority of the times that I'm doing. Obviously, when you're flipping 2 coins, sometimes you're going to get 2 heads, sometimes you're going to get 2 tails, sometimes you're going to get a head then a tail, sometimes you're going to get a tail then a head. But on average, you would expect to more often than not get 1 head when you're flipping a coin. moving on. Number 3, a club sells raffle tickets for $5 each. There are 10 prizes of $25 and 1 prize of $100. If 200 tickets are sold and you bought one of them, then what are your expected winnings? How much on average is the club profiting per ticket? So I'm going to buy some tickets, and there's 200 tickets being sold. So out of 200, 10 people are going to win $25. Okay, one person is going to win $100. Everybody else is going to win $0. Okay, so X represents how much money you can win. The probability of X, we need to figure that out. So the $100 is probably the easiest one because there's only one prize of $100. You're selling 200 total tickets. So we would say 1 out of 200 people are going to win $100. 25 is also pretty easy because I said there's 10 prizes of 25. So that means 10 out of the 200 people are going to win $25. The 0 is not given to us. We've got to go ahead and figure out, okay, so how many people aren't going to win anything at all? And so if we have right now 11 people that are going to win, we have 10 people going to win 25, and then we have one person who's going to win 100. So it's 11 total winners. That means we have 189 people that are going to lose, because what you want to do is you want to take your 200 tickets that are totally sold, subtract the 11 people who are going to win, and that leaves you with 189 that are going to lose, or they're going to win absolutely nothing. So that's going to be our 0. So we're going to say that's going to be 189 out of the 200. On the calculator, one thing I really like about putting the stuff in the list is that the list can even handle fractions. I don't have to convert those to decimal. It can handle that for me. So in list 1, I'm going to put my X's, which are the total amounts of money I could win. I could win 0, I could win 25, or I could win 100. Okay, next to it, I'm just going to put the fraction and let the calculator deal with changing it to a decimal for me. So I'm going to do 189 divided by 200. That's how many people are going to win $0. Then I'm going to do 10 out of 200. That's how many people are going to win $25. And then I'm going to do 1 out of 200. That's how many people are going to win $100. And then again, I'm going to do stat, calc, one variable stats. List 1 is in my list, and then list 2 is my frequency list. So then I'm going to calculate. And so $1.75 is the expected value. So the expected winning, if you will, for each person on average is $1.75, which kind of probably doesn't make a whole lot of sense conceptually, because 189 people are going to lose. They're not going to win, $1.75. But that one person that's winning $100, it kind of averages out to everybody else. And so that's why it's like the ticket is kind of expected value of $1.75, even though realistically you're either going to lose, you're going to win 25, or you're going to win 100. But because you have, all of these people, the 11 people that are winning, it averages out to $1.75. So kind of different. But the question goes on and says, how much on average is the club profiting per ticket then? So the club is selling the tickets for $5 a piece. And so on average, they're having to give out $1.75 to each person, theoretically. And so if we take the $5 that they're paying for the ticket and we subtract the $1.75, then the club is expecting to profit $3.25 for each ticket that they're selling. Okay, so $5 minus the $1.75 that you're expected to win leaves you with the $3.25. Okay, and again, that's how much the club is profiting per ticket. Okay, moving on, number 4. Insurance companies compute expected value so that they can set their rates at profitable but competitive levels. A 64-year-old man obtains a $10,000 one-year life insurance policy at a cost of $600. Based on past mortality experience, the insurance company estimates that there is a 0.963, so that's 96.3% chance that this man will live for at least 1 year. How much can the insurance company expect to earn on his policy? So they're either going to have to pay this man, or they're going to get to keep all their money. And so if the man dies, and I'm actually going to do this chart kind of backwards here. I'm going to do the x, and then I'm going to do the p of x. The probability that he dies, well, I'll start with lives. The probability that he lives, let's do that one first, because that's what's given to us, is 0.963. So then what's the probability that he is going to die? So we would do 1 minus the 0.963. And so if he 96.3% of the time is going to live, then 3.7% of the time he's going to die. Okay? And so let's think about what the company actually has to pay out if you live versus if you die, or how much they're going to profit. Okay? Because it says how much can the insurance company expect to earn. So we really only care about the insurance company. So let's see, he's going to pay $600 to the company no matter what. And so the insurance company is hoping that they can just make $600 off of him, because they're going to make the $600 off of him, and they don't have to pay him anything out because he's going to live. The other side of it, though, is that he is going to, if he dies, then he's going to still pay them the $600 before he dies, but they're going to have to pay him $10,000. So for the company, that is a positive $600 that they're getting in the beginning, but they're having to subtract the $10,000 that they're paying out. So the company, for anybody who dies, is actually in the hole $9,400. They're not out the full $10,000 because you did pay $600 up front for the policy, but they're still out the $9,400. You might be saying, wow, you know, how can insurance companies stay in business? You have to look at the fact that that only happens 3.7% of the time. The majority of the time, you know, way more than the majority of the time, they're making $600 off of most of the people that they're insuring, because they don't die, and so they get to make a lot more money. So well, let's see if they get to make a lot of money. So what I'm going to do is I would do stat edit, and in my list 1, I want to put the x's, and then in list 2 the probability of the x's. So I have 600 as a possible amount that the company could get, or negative 9,400 is the other amount that the company could get. And then the probability of them getting 600 is 0.963. And then the probability of them getting negative 9,400 is only 0.037. Okay, so then I'm going to stat calc, one variable stats, list 1, list 2, and then down to calculate. And so the company is profiting on average $230. Okay. How much can the insurance company expect to earn on this policy? Their expected profit off of each and every single insurance policy that they're able to sell, their profit is only $230. It's still a profit, so it does add up when you have a lot of people that you're insuring. But you know, what brings it down from that $600 is the fact that sometimes they do have to pay out, and so that, you know, it does bring down their expected earnings. Okay, I believe this will be the last one. Let's go. A Wheel of Fortune at a carnival is divided into 5 equal parts. Each spin costs $1. Because every child must be a winner, a prize is received for each number spun. If you spin and get a 1, 2, 3, or 4, you win a piece of bubble gum. It's individually wrapped, of course. If you spin and get a 5, you win a king-size candy bar. On the average, how many spins will you have to do in order to win the candy bar? Use the random digit table below to simulate the spin 20 times. Then find the average number of spins. So we really don't care about winning the bubble gum. We just care about winning the candy bar. And so there's different ways you can do this. There's 5 equal parts of the spinner, and so you want to assign your digits to basically be 20% a piece. So like 1 is 20%, 2 is 20%, or the section. Section 1 is 20%, 2 is 20%, 3 is 20%, 4 has a 20% chance of winning, and then 5 has a 20% chance of winning. So I think what I would probably do is say, okay, I'm going to assign that if I see a 0 or a 1, then that's section 1. So if I see a 2 or a 3, that means section 2 was landed on. If I get 4 or 5, then that's a section 3. And so 6 or 7 is section 4. And then 8 or 9 is going to be section 5. But the one that, really the only one that matters is getting the 5. Because if you spin and get a 5, you get the king size candy bar, and they want to know how many spins it takes to get the candy bar. So with that in mind, you really could make this more basic and just say, you know what, I'm going to do 0 through 7 is losing, not getting the candy bar. It's a loss. And I'm going to do 8 and 9 as a win. And that should work for you, because that means you're giving 20% of the digits to be a win of the 5, and you're giving 80% of the digits to be a loss of you're getting either a 1, 2, 3, or 4. Okay, so you're going to keep going until you get a 5. You're going to read one digit at a time. And let's see, we're going to read one digit at a time. And I said until you get a 5, but what I actually meant was until you get an 8 or 9, because 8 or 9 represents the section 5. So I'm going to read one digit at a time and stop when I get 8 or 9, because that is a win. Okay? Does it tell us how many trials to do? So let's do it 20 times. Okay? So I'm going to stop when I get an 8 or a 9. So right here, I stop. Remember that we are paying $1. Doesn't really ask us how much. I guess it doesn't matter. On average, how many spins. It's just saying. So, okay. So before I got the 8, it was 1, 2, 3, 4, 5. It took me 5 times, and then I won the candy bar. Then the next time I do it, it's 5, 10. It looks like it takes 14 times to win the candy bar. Okay, next time I do it, it only takes 1 time to win the candy bar. The next time I do it, it takes 4 times to win the candy bar. Okay, next time. Let's see, that's 5. It looks like 10 times to win the candy bar. And then here we are. The next one looks like 11 times to win the candy bar. Here we have 3 times to win the candy bar, 1 time to win the candy bar. Remember, you're looking for 8s or 9s. There's 5. That looks like 10 right there. There's another one, 4. So 2 times this time. Let's see, we got to do this 20 times. I've done it 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11. I've done it 11 times only. Okay, so here's another one. That's 12, 13, 14, 15, 16, 17, 18, and 19, and 20. Okay, I'm going to get to stop for real after that one. So let me go count up how many I had to do. So there's like 5, 6, 7, 8. This one took 2 times. This one looks like it took 3 times. Don't forget to count the 1 and the 5 on the end there. So 5, 6, 7, 8, 9, 10, 11, I think. 4 and 9 is 2, and then we've got 9 for this trial, 4 for this trial, only 1 for that trial, and 8 for this trial. So now we've got to put that into the chart here, and unfortunately my ink is going to stay on the smartboard and not move with the worksheet. So bear with me, it's just going to kind of be at the bottom, and we'll have to use it to count here. Hopefully I'll be able to figure it out. To put my tally marks. So total number of spins that it took. Did we ever get a 1? So I think I have a 1 right here. I have a 1 right here. And a 1 right here. So it looks to me like I have 3 tally marks, which is a frequency of 3. Remember, we did it 20 times. So that would be 3/20ths for a probability. Okay. Did we ever do it in 2? Let's see, there's 1, 2, 3. It looks like only 3 times that I did it in 2. So 1, 2, 3, 3/20ths. Did I ever do it 3? So here's a 3, and then there's a 3 down there on the end. So that's 2 times. 2/20ths would simplify to 1/10. And then I do see a 4, and another 4, and another 4. So it looks like I only have 3 of those. Okay, so that needs to be a 3, which makes it 3 out of 20. I do have 1 5. So tally, and it's 1/20th. And then it doesn't look like I have any 6s. It doesn't look like I have any 7s, but I do have some 8s. So I have 2 different 8s here. So 2 tallies, 2, and remember 2/20ths simplifies to 1/10. And then I do see 1 9. So 1/20th. I see 1 10. So 1/20th. I see 2 11s. That appears to be all. So it's 2 11s, which again is 1/10. I don't have any 12s, I don't have any 13s, but I do have a 14. It looks like I missed a 10, which is kind of nice when you circle things because now I'm, looking at what's left over, but I did miss a 10. I can go back and correct that. So I have one more tally here, which makes this 2 10s, which makes it then 1/10 instead of 1/20th. So let me see if I can fix that without messing up too much stuff. This was a 2, this was a 2, so now this is 1/10, and this is 1/10. And I do have the 14 that's, off the chart there. Sorry about that. I'll just write it over here because I do want to go back and double check and make sure I got them all. And the way I'm going to make sure I got them all is I'm going to add up all my tallies and make sure it does add up to 20. So cross your fingers for me. I hope it works. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Good. I have 20 tallies. So determine the average or expected number of spins needed until you win the candy bar. So I would go over here on Stat Edit, and the possibilities were 1 through 14. So I'm just going to put them all in. Did that kind of quick, so hopefully I got them all. Kind of nervous, but we'll see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. At least what's on my screen looks good. So 1 had a 3 out of 20 chance. 2 had a 3 out of 20 chance. 3 had a 1 out of 10 chance. Right here, guys, if you accidentally didn't simplify and you did 2 out of 20, it would be fine because it would still be that 1/10. So you would be fine. It wouldn't be a big deal, okay? Just for me, I like you to do simplified fractions. 4 is going to be 3 out of 20. 5 is going to be 1 out of 20. 6 didn't happen, so what should we do? You can do 0 out of 20, or you can literally just put 0, because 0 over 20 is obviously going to be 0. 7 didn't happen, so we can put a 0 there to represent that. 8 would happen 1/10 of the time, or again, you can put 2/20ths. It's not going to hurt anything. 9 is going to happen 1 out of 20 times. 10 is going to happen 2 out of 20 times, which is 1/10. And then 11 is also going to happen 2 out of 20 times, which is 1/10. 12 doesn't happen, 13 doesn't happen, and 14 happened 1 out of 20 times. Okay, so then I'm going to go stat calc, one variable stats, and I'm going down to calculate. And I got 5.65. So what on earth does that mean? It means on average, I need to spin the wheel 5.65 times, which is not really even feasible. You can't spin it 0.65 of a time. So if you want to say, according to expected value, in order to kind of guarantee myself that I'm going to win, I really need to spin it at least 6 times, because on average, it should take about 5.65 times to spin the wheel before I'm going to win. So I'm going to get a candy bar if I've done it at least 6 times. It should cover it. Is that a guarantee? No. But according to our simulation, according to our random digit table, that's how many times it takes should take to win the candy bar. So I hope that kind of clarified those examples a little bit if you take the time to watch the video. Have a good weekend.